Our next talk is by Dowdall. We'll be talking about abstract commensurators, big mapping class groups. Thank you. Thanks to the organizers for inviting me to put this great workshop together. And thank you to Rafi for all the great setup for big mapping class groups. Anyway, so this is a project joined with Juliette, Bavard, and Kasra, Rafi. Yeah, let's just get started. Okay, so here S will be a surface. And as in Javi's talk, it'll be always connected, orientable, and I want to assume the boundary is empty, okay, but it could have punctures and so forth. And I want to distinguish between two different regimes for the finite-type case. So that's where the fundamental group of S is finitely generated. Okay, so in this case, as Rafi was telling us, there's a very nice and simple classification of surfaces. Your surface is determined by the genus and the number of punctures, which are just two non-negative integers. Okay. In contrast to that, there's the infinite type case. So that's when the fundamental group infinitely generated. Okay? Very good. So let me start by find the mapping class group. So I also like mod instead of map, even though in our paper I think we use map. Anyway, let's use mod. Right, so the mapping class group, that's the homeomorphisms of the surface, mod homotopy. And for the purposes of this talk, I'm going to be thinking of the extended mapping class group. So I also include in there orientation of reversing homomorphisms.
I have a sort of stupid technical question. Does homotopy imply isotopy even for infinite type surfaces?
Dan is nodding his head yes. Okay. I think so, yeah. Okay, so let me remind you of some classical results. From the finite type world. So here, let's assume S is finite type. And just to kind of rule out some exceptions, let me assume, to be safe, that 3g minus 3 is at least 4. Oh, plus n is at least 4. Okay, and then similar things as to what I'm going to say are also known for the other surfaces, just with some modifications. Okay, all right, so here are the classical results. First of all, that due to Ivanov back in the 80s, and also to McCarthy. 6, I think Ivanov's paper was first, but published later. Anyway, it says that the automorphism group of the mapping class group is the mapping class group. Okay, so there's a map from the mapping class group into the automorphism group given by conjugation that maps onto the inner automorphism group, and in this case that's an isomorphism. Okay, so that's the theorem. All right, and I think I can write it here. So that's one theorem. The other theorem is kind of a folk theorem, but it follows from, without being written down, from work of Berman, Lubatsky, and McCarthy, combining that with paper of Herrer, says that the mapping class group determines the surface, basically. So if I have an isomorphism, between two surfaces, between S and mapping class group and the other surface S, is always, so this is an isomorphism, is always determined by a homeomorphism. Okay, so if you have two different surfaces, finite type, and their mapping class groups happen to be isomorphic to each other, then the surfaces have to be homeomorphic to each other. Okay, so the surface determines the mapping class group determines the surface. Okay, so that's two very nice results. results. And so today, what I want to think about is these sorts of things hold in the infinite type case. Okay, so what about big mapping class groups? Okay, so by big, I mean mapping class group where S infinite type. Okay. So to be more precise, my questions are: can you calculate the automorphism group of the mapping class group? And secondly, does the mapping class group determine S? Okay, so those are two questions you might ask. Okay, so and let me tell you first what was known, so the first result along these lines, which is due to Patel and Blemis in the same paper that Javi was mentioning before. So Patel and Nick Blemis last year, they proved that if S has finite genus, at least 4, then any isomorphism from the pure mapping class groups of S to the pure mapping class group of some other surface is induced by a homeomorphism.
So S prime doesn't need to be the answer.
Well, it does in the end,
Right.
but yeah, as for the hypothesis, it doesn't need to. Yeah. Okay. Right. So that was, very interesting results along these lines. And that kind of motivated us to look into these questions. Let me, I guess, just tell you our theorem. The main theorem that we're going to talk about is again with Juliette, Bavard, myself, Kasra, Rafi. So from last year, let's suppose S1 and S2 infinite type surfaces. Again, you could maybe only assume one of them was infinite type if you wanted to. Anyway, that's formulated. Okay, let's let phi be an isomorphism between G1 and G2, where G1 and G2 are finite index subgroups of these mapping class groups. Okay, so you have your two surfaces, S1 and S2. You choose your two favorite finite index subgroups, and you take any isomorphism between them. Okay, so then the theorem is that there exists a homeomorphism, call it H, from S1 to S2, inducing phi. So, by which I mean that phi of any mapping class group element F is given by H, F, H inverse. Okay? So in particular, the surfaces are homeomorphic. Okay? So that answers this question, yes. Okay? Because you could take the G's to be a whole mapping class group and stuff. Okay. All right, very good. And let me, so the title has something about abstract commensurations. So let me.
Does it also answer that first question?
We're getting to it. In 2 minutes. Okay. So a commensuration of a group G is an isomorphism between finite index subgroups. Okay, so commensuration is usually two finite index subgroups and an isomorphism between them. Okay, that's the definition of commensuration. When we define the abstract commensurator, the group, so that I call comm of G. This is the group of equivalence classes of commensurations. Okay, an equivalence class here just means that two commensurations are equivalent if they agree on a finite index subgroup. Okay, so you have an isomorphism defined on one finite index subgroup, I have one defined on another finite index subgroup. Their intersection is a finite index subgroup. And if I could pass to a further finite index subgroup where they're the same isomorphism, then they're equivalent. Okay, and this forms a group under composition. If I take two things, I can compose them by passing to further finite index subgroups and so on. Anyway, so that's the abstract commensurator. And just to give you like a little bit of flavor about it, so you have a natural map from the automorphism group to the abstract commensurator of the group, because any automorphism of the whole group itself is a commensuration. That's fine, so you get a map like that. But generally, this group you might expect to be a lot bigger, perhaps. So for example, for the automorphism group of the integers, well, it's not very many automorphisms. I can either just do the identity or flip. Okay, so that's z, mod 2z. But for the abstract commensurator of the integers, well, the finite index subgroups are just given by numbers, and any two of them are isomorphic by one thing. So this is actually a pretty good group, and it's isomorphic to the group of the multiplicative group of the rational numbers. Okay, so this is finite group. This is not even finitely generated. So it's much bigger. Okay, right. Okay, so the abstract commensurations of the big mapping class group we get as a corollary to this theorem. So if S is infinite type, then let me just mention two things. So first of all, out of G will be finite for any G finite index in the mapping class group. So the theorem says if you take any finite index subgroup, you have an automorphism from G to itself. Well, it's just induced by some automorphism of the whole group. Again, it's a finite index subgroup, so there's the index there is finite. So that's one corollary. And then the second corollary is that these natural maps relating the mapping class group to its automorphism group to the abstract commensurator are all isomorphisms. So we have natural isomorphisms from the mapping class group to its automorphism group to its abstract commensurator. Okay, so yes, this also answers the first question. I'll go right over here. It's equal to that. Right, so I view this sort of fact that the group has the property that it's equal to its own abstract commensurator is kind of a evidence of sort of algebraic rigidity in some sense, that there's like very, very few isomorphisms at all, even up to finite index subgroups. All of the ones are the ones you have to have from conjugation. Okay, so it's very algebraically rigid. Okay. That's another consequence, yeah. So, so as Javi was telling us, there's lots of kind of subtle things about the topology in this mapping class group. You could think of it, if you wanted, just as a sort of discrete group where you could give it this topology and have a compact open topology. And you might wonder whether or not, and automorphism of the mapping class group that was just an algebraic automorphism had to be continuous with respect to its topology, and this says the answer is yes. So, because it comes from conjugation, and that preserves the topology. So all automorphisms are automatically continuous. Okay. All right, so that's the results. I want to spend the rest of the time discussing the proofs. Before getting to that, let me just make kind of one remark about sort of the issues and difficulties that arise in going from this sort of classical setting to the big mapping class group setting. And so we already saw some of this, but the remark is basically just that big mapping class groups are sort of much bigger. Finite-type ones. Okay, let me make just a little table here. Okay, so this is the finite-type. So it's not there's no argument. It's just an abbreviation for mapping class group. Right, so first of all, so in the finite type setting, the mapping class group is, of course, finitely generated. In contrast, the big mapping class groups are uncountable. Okay, so in particular, they can't be finitely generated or even countably generated. Okay, so they're bigger in that sense. We've already seen this kind of topology, so this is a discrete group. And these have a non-trivial topology from compact open on homeo. Okay, and then the sort of biggest issue for this these questions here today is the fact that in the finite type situation you have sort of normal forms. Okay, so you have normal forms for elements. Let me remind you that this is Thurston normal form. So S, finite type surface. So there's a constant C such that for any element of the mapping class group, if I look at f raised to some power, c, some fixed number c, then it always looks a certain way. So it looks like something like this. Okay, so all these genus everywhere. And what I can do is find some subsurfaces. So maybe some curves here, maybe there's a curve there, maybe there's another curve there. And I have these subsurfaces so that I break it up. And maybe here I'm doing something like a pseudo-Anasov. Maybe here I'm also doing a pseudo-Anasov. Over here I'm the identity on these pieces, and I'm maybe twisting. You know. And then here you're maybe twisting. Okay? So after raising to a power, you can decompose the surface by cutting on some curves on the components. You're doing pseudo-Anasovs or the identity, and then maybe you're twisting on the curves. Okay? And everything looks like that. So it's like a picture that tells you what everything looks like. And as far as I know, there's no such thing known here. Okay? So, and this is a real problem because, we'll get to this in a second, but basically the key thing is you're going to have be able to identify Dane twists and say, like, here's an element, and if it satisfies these properties, it's a Dane twist. And here, like, here's this mystery element, I know what it looks like, and I can check if it satisfies those properties. And here, I don't have any idea what it looks like, so I have no idea what property it satisfies. Okay, so that's kind of the problem. All right, let me now go on to the proof of the main theorem. Right, so there's two main ingredients. Okay. So one is, as I just said, algebraically identify Dane twists. Okay, and sort of the classical result that I mentioned before, this is done very much by using the ideas of a normal form and so on. And the result of Tell and blindness that I mentioned here, so I mean, they have to deal with this somehow. And what they do is that in this situation, finite genus most 4, they come up with a sort of new topology that they put on the pure mapping class group here. And by using that sort of Dane twist topology, they're able to characterize Dane twists. So that's kind of, you have these nice things, you have these maybe things you are worse. So they're like using this non-trivial topology in like a way to their advantage to sort of this problem of characterizing Dane twists. And what we do instead is we use this somehow. And we use this fact that the group itself is uncountable. And we'll use that to help us identify the Dane twist actually. So we'll see how that's done in a second. All right, so the second ingredient is this curve complex rigidity that Javi already mentioned. So let me just remind you. And okay. Hernandez, Morales and Valdez. I'm spelling them wrong. Morales, Valdez from last year. And let me just attribute it to them. Their paper was before ours version, so maybe we can prove this first. And they said that any simplicial automorphism of curve complexes so here, say S prime infinite type surfaces, any simplicial automorphism of curve complexes is induced by homeomorphism. All right, so those are two ingredients needed to prove the theorem, and what I want to do now is just use these and prove the thing. Okay, so theorem is again you're given an isomorphism between finite index subgroups. Okay, so I have two finite index subgroups, G1 and G2. And I have some isomorphism between them. All right, so now if I have a curve, alpha, so I use C0 for the zero skeleton of the curve complex, so that's just the set of homotopy classes of curves. Okay, so for every curve, I have the Dane twist, D of alpha, and since G1 is a finite index subgroup, this is an infinite order element, so I can raise it to some power, like the index of the group, so that it will be in G1. Okay, so for every curve, I have the Dane twist of the K is in G1. Well, the fact that you believe I can algebraically characterize Dane twist says that, well, if I take this curve and I look at its Dane twist, and I apply my isomorphism, that sends it to some element in the other mapping class group. Well, I can also characterize Dane twist there, and this satisfies the same characterization because it's an algebraic automorphism here. So this is also a Dane twist. So this is a power of a Dane twist for some curve, h of alpha, in the curve complex of the second surface.
If you're characterizing non-separating twists.
I think just all twists. There's a list of criterion that tells you if you satisfy these criteria for your Dane twist.
How do you get H then?
So there's no, H is just a,
oh,
this is just an assignment.
Oh,
it's just a set map.
Got it.
I don't know what H is.
Got it.
I don't know what H is. Okay. Yeah. So I just know for every curve there's some alpha, there's some H of alpha over here. So that's all I have. Okay, so I get a bijection H from the set of curves on the first surface to the set of curves on the second surface. And it's bijection because I can go back and forth. Okay. All right, so now, this H actually has to be simplicial. Why is that? Well, just two Dane twists, mu. If and only if alpha and beta are disjoint. Okay, so if I have my two Dane twists, I have these two things that I raise to power. If these alpha and beta are disjoint, these two things commute. They go to two things commute, to those two Dane curves have to be disjoint. Okay, so it's a simplicial map. So the curve complex rigidity implies that H is an automorphism. Or sorry, so wait, H is simplicial, so H comes from homeomorphism. Okay? Right. So there, it has to extend separating things to not separating things. All right, so already we see from this that if you have mapping class groups are isomorphic, then the surfaces are homomorphic. Okay, but now we have to do this business of actually showing H induces the isomorphism. Okay, so that's, you think it might be hard, okay, but it's actually very easy, and there's this great trick that Ivanov used in his sort of original argument that I just want to tell you because it's so nice. Right, so now, for any f in G1, okay, so that's in the first mapping class group, I can do the following thing. So let me take my Dane twist around some curve alpha, and I can conjugate this by f. Okay? Now on the one hand, if I take a Dane twist and I conjugate by f, that's another Dane twist. That's a Dane twist around f of alpha. Okay? And we already know that this, it's some Dane twist around a curve, so it's equal to a Dane twist around some other curve, and that curve is called h of f of alpha. For some, it doesn't really matter what I put there. Okay? On the other hand, this is an isomorphism, so I can do the conjugation outside. So this is instead this. Okay? Now this thing here was again a Dane twist, and I'm conjugating it by something. So that's a Dane twist around a curve that I know. It's the curve phi of f applied to h of alpha. This is the Dane twist around h of alpha, and I'm conjugating by phi of f. Okay, so for every curve, I know that the Dane twist to some power of h of f of alpha is equal to the Dane twist to some other power of this curve. Okay, so that says, that curve has to equal that curve. Okay, the Dane twists are the same. All right, so phi of f of h of alpha is equal to h of f of alpha for all alpha. Well, that implies that phi of f of beta is equal to f of h, wrong way, h of f of h inverse of beta for all curves beta in the curve complex of the second surface. Okay, and then there was this Alexander sort of method that Javi mentioned before that implies these two maps are the same. Okay, so then the Alexander method implies that phi of f is equal to hf of h inverse. Okay. All right, so that's the okay. So now, let me go on and tell you something about the two ingredients. Okay. So, yeah, so let's start with the curve complex rigidity. Okay, so as I said, this was first proved by the other group of people, and then we gave a different proof, and I kind of like our proof, so I just want to tell you. Anyway, so okay, so alpha, let's say, is a simplex. So this is a simplex in the curve complex of some surface. Okay, any surface, doesn't matter, right? So I want to put an equivalence relation on the link of alpha. The link of alpha is the set of all curves in the curve complex such that that it's adjacent to each one of these curves in my simplex. Okay, so all the adjacent ones. Right, so that's the link. And here's the equivalence relation. Okay, so I have two curves, gamma and beta, in the link. They're equivalent if and only if there exists a third curve, delta, in the link, such that beta and delta are non-adjacent, and gamma and delta are non-adjacent. Okay, so two things are equivalent if I can find some third thing that intersects them. Okay, and then this is just a very simple kind of observation that the equivalence classes of this link pick out the complementary components. Okay, so the equivalence classes link of alpha are the curve complexes for S prime, a component of S minus alpha. So I take this finite list of curves, I cut on them, I have some number of complementary components. For each one has its own curve complex, and that's exactly the equivalence classes of the link with the induced simplicial structure. Okay? All right, and the proof of that is just, you just maybe think or draw one picture. So here's a surface, for example, and I was told I couldn't use certain colors. I don't know what colors I can use. Try a bunch. Okay, so maybe alpha is like this curve here. Maybe this is alpha 0 and alpha 1, and I have some other curves in the link, and I want to try to decide if they're in the same equivalence class or not. Okay, well, let's look at and in this curve, delta. Oops, no, I want that to be gamma. Sorry. And this curve, beta. And the question is, are they in the same equivalence class? Well, yeah, look, here's a curve, also in the link, that's not adjacent to both of them. Okay? And look, they're in the same complementary region. And if instead I had delta over here, this was delta, some other delta, oops, gamma. Okay. Then obviously I can't find some curve that intersects beta and gamma, and that also lives in the link. Okay, so there's the proof. Okay. Great. All right, so once you know that, you can just prove this rigidity result by some finite sort of type exhaustion of the surface. Okay, so what I do is I take a sequence, alpha 1, alpha 2, alpha 3, etc., of multi-curves. And my first surface, S, such that, say, exactly one component, we call it y, I, of S minus alpha I, has finite type. Okay, so I take these multi-curves, and each one they cut the surface into some components, and one of them is finite type. We call that yi. And furthermore, such that these yi's are nested in this way, and the whole surface is their union. So they give an exhaustion. Okay, and you can find a sequence of curves that does that. Okay, now, if I let epsilon I be the link, or be the equivalence class of yi in the link of alpha I. Okay, so yi is a component in the complement of alpha I, so it's one that corresponds by this theorem to one of the equivalence classes of this link, and I call that epsilon I. Okay? So now if I have some automorphism between these curve complexes, then I can restrict to epsilon I, which is some subset. It's a equivalence class of the link, and that gives me a map from epsilon I, and since it's a simplicial automorphism, and this was some equivalence class of a link, it has to go to equivalence class of the link of the other thing. So this has to go to epsilon prime, which is equal to the equivalence class of the link of the image corresponding to some component yi of S prime minus the image multi-curve. Okay? So now, but the theorem also said that this equivalence class is the curve complex with the induced simplicial structure. So I get a map like this. Okay? And now what I have is a so this was an automorphism, it restricts to an automorphism here, so this is an automorphism of these curve complexes of finite type surfaces. So the classical result says that I get a homeomorphism, hi from yi to yi prime, which is sitting inside of S prime.
So how do you know that y prime is finite type?
Well, because its curve complex is isomorphic to this curve complex, which has finite clique number. So that's fine.
Yeah.
Okay. And then now I can just take a direct limit of these homeomorphisms, and it gives a homeomorphism H from S to S. Right. So that, all of that is, in some sense, very similar, and in some sense, using the classical things. And this argument is very similar to the argument, the original argument in the finite type situation. Surely the new thing here is having to do this algebraic characterization of dangerous. So let me finish by explaining that. Okay, and it turns out that, in my little table here, see, there's no normal forms in general, okay? But in the finite type world, there is normal forms. So if you could somehow figure out which elements are supported on some finite type surface, then they have kind of a normal form. So the key is to figure out which elements are supported on a finite type subsurface, okay? So here's the definition. You say that F, an element of the mapping class group, you just say has finite support if there exists a subsurface such that it's the identity outside of the subsurface. So let me write that as f of beta is equal to beta for all simple closed curves, beta in the complement of y. So all curves that aren't in y are fixed, so I'm the identity out there, and I'm really just a word of them.
You want y to be compact.
I want y to be finite type. Yeah, sorry. So it could have, it doesn't have to be compact, it could have functions. But finitely many. Okay, so the key proposition that we prove that makes these things work is a characterization of this property algebraic. Okay, so suppose G is a finite index subgroup. Then, and that F is in G, then F has finite support if and only if the conjugacy class of F is canonical. Okay. So again, here we're using the fact that the whole group is uncountable. So this like a lot of room is letting us sort of help determine the bad guys. All right. So so that's the key proposition. Let me give it. Okay. So first of all, let's suppose F has finite type support. Okay. So then it's you could just think of it as coming from this finite type subsurface Y. In that case, the mapping class group of Y is generated by Dane twists. So F is a finite product of Dane twists. Okay, so here F is a finite product Dane twist. And the same holds for any conjugate of F. Okay, there's only countably many Dane twists. Okay, so there's only countably many Dane twists, there's only countably many finite products of Dane twists, and everything in the conjugacy class is one of them. Okay, so the conjugacy class is countable. Great. Okay, so let's do the other direction. Alright, so suppose F has infinite support. Okay, so now what I want to do is I want to find a sequence alpha 1, alpha 2, alpha 3, etc. of simple closed curves on S such that the following thing holds. So these alphas, they should all be disjoint. Okay, and each one should not be fixed by F. And furthermore, if I look at F of alpha j and alpha I are disjoint if I is not equal to j. So they're all disjoint except possibly alpha I and F of alpha I. Okay, and how do I find a sequence of curves like this? Well, the assumption is it doesn't have finite support. So any finite type subsurface you look at, there's some curve outside of it fixed. So I pick some alpha 1, and then I pick a farther out alpha 2 that doesn't involve alpha 1 or its image, and then I pick something farther out, and so on that's not fixed. And I keep picking things that are not fixed that are farther and farther away. Okay? So I do that. Now, let me fix an I such that the Dane twist around alpha I is in G. I have this finite index subgroup G hanging around. Get this finite index, so any Dane twist I can raise to some power so that it's in G. Okay? Now, for each sequence, sigma, so that's sigma 1, sigma 2, etc., where the sigma i's are plus or minus 1. So for every list of plus 1, minus 1, etc., let phi sub sigma be the following product of Dane twists. Okay, so all these Dane twists to the ni are all in G. These are all disjoint curves. I can raise them to the plus power or minus power as I choose, and this is some element language. Okay. So now what I'm going to do, notice that there's uncountable many of those things. Okay. And now I can use those to conjugate F. Okay, look at the conjugates. and these are all distinct. Okay, let me not write down the calculation. Okay, it's something you could check on your own. The point is just, since I know what f does to these curves, if I, say I write this thing times the inverse of some other conjugate, okay, then I can just write that as a product of these exact twists, alpha i's and the f of alpha i's, and I know when they're disjoint, everything cancels, and if sigma and some sigma prime are different, then not everything cancels. Then you can just see they're all distinct. Okay. Right, so there you go. So that's uncountably many things in the conjugacy class. Great. Okay, just a couple minutes left. Let me now try to finish explaining how to use this to algebraically characterize dangles. Okay, and I maybe don't have enough time to say the whole thing, but I think I can at least write down the list of conditions. Right, and in some sense, really after you have this, doing the algebraic characterization of Dane twist is really in the same spirit as what was done in the past in the classes. Okay, so anyway, but let me try to write down the characterization. Okay, so I'm given G, finite next subgroup. Let me let f sub G be the things in G such that the conjugacy class is countable. That's a subgroup G. Okay, that's a thing I can check algebraically. Okay, so great. Right. So now have a kind of proposition here. So f in G is a primitive Dane twist. By primitive, I mean, any Dane twist, I might have to raise it to a power to be in G. So I mean the least such power, so that it's in G. Okay? It's a primitive Dane twist, if and only if the following conditions hold. So first of all, f has to be in this set f sub G, which I can characterize algebraically. The Dane twists obviously have finite type support. Okay, good. So that's one. Two, if I look at the center of the centralizer, that this is generated by f and is isomorphic to z. Okay, so this is the centralizer of f and g, everything that commutes with f. I intersect that with this subgroup of things that I sort of understand, because if you're not in here, I kind of don't understand you at all, because I have no normal form. Okay, and then I look at the center of that. Okay, and the condition is that that center should be infinite cyclic generated by f. Okay, so it's an algebraic condition. Okay, the third one is that if I look at these centralizers, they are the same when I raise them to powers. I mean, think about a Dane twist. If I have a Dane twist and I have the Dane twist with 10 power, they have the same centralizer. Okay, so I like that condition. And then let me call these conditions collectively M. Let me just add. So this,
Yeah, I have a question. Do you need this FG so then before it becomes Z, the centralizer becomes G?
do I
If you
need
make
what?
it bigger, then the centralizer becomes smaller, right? What's wrong with
Oh, yeah, oh. I think I might. Sorry. So, wait, I'm jet lagged.
So then one more condition. So now that I've done that, I can look at M sub f. I call M sub f the set of all things in M. So M is the set of things satisfying these things, which I can identify algebraically. So I look at the set of things in M that commute. Okay? So I can now look at that set, and I want this to be maximal in the collection of all such things. Okay? So that's what you want. All right, so that's the characterization. Let's see, so I'm basically out of time here, so maybe I won't explain it, but basically the point is the following thing. If you're in here, then it turns out you can have this, like, pick out this canonical multi-curve, which is like the boundary of the support of your Thurston normal form or whatever. Okay? And then, so you assume that. Then you take anything in here, so anything that commutes with you has to preserve that curve. Okay? Because it commutes with you, so it has to preserve this canonically defined multi-curve. So then you show that the Dane twister on that multi-curve is in the center. Because, you know, it commutes with anything that thing. So if you assume the center is cyclic, then that Dane twist around that multi-curve is u, or a power of u. Okay? And then, and this like kind of says you're primitive. Okay? Because like if you raise, you know, well, anyway. And then this is, so your multi-curve might have many components, and this is picking out the things that have one component in the multi-curve. So if you think about like if you're a Dane twist around several things, well, you're in the set, and this thing will be smaller than if you had just one of the guys. Because that's the separate things that are missed. Dane twist around single curves, and that's the characterization. All right, thank you.
Other questions for Spencer?
Can you give me an example or convince me that one exists of a finite index subgroup of a mountain class group of infinite type surface?
Fine. Sure. I mean, like, one example would be, like if you took that surface, you could look at its like pure mapping class group.
Okay.
For example.
What about if I replace my question with pure mapping class?
The last talk had maps to see.
Oh yeah, sorry. Yeah.
Take
No, that's fine. Thanks.
Wait, what? That's infinite index.
Oh, sorry. Z is.
You can't map to a finitely generated group. You have to map to a finite group.
That maps Z to a finite.
Yeah.
Oh, I'm sorry. I decided.
Finite covers. Oh, that's
Take any map and pattern surface to finite group.
Sure.
Oh yeah, this is still a free group, right? Yeah. So, yeah, they're all free groups. Yeah. Yeah. I have a question actually. So you do have your theorems about the whole mapping class group, and I guess it's no longer the case that the pure mapping class group is finite index. So
We also prove it for the pure mapping class group.
great. Okay.
Just too many things to write. Yeah. Yeah.
In the middle column at the bottom, you've got an infinite product of things in G. So how do you know that's in G?
Well, yeah, so that's a good question. Let's see. I could use this power, I could like, I could take the infinite product and just raise it to the power. There's like the same power that works for all the curves if I wanted to. And then that was an infinite product, it's certainly the mapping class group would raise the power. I can't do it?
But they're all additional support.
It's just that you write it down on the.
No, it's clear it's a mapping class. The question is why is it in D?
Why is it in G? G is a finite index subgroup. Raise it to a power.
Yeah, take it to a power.
Yeah, to a power. So it's in G.
Yeah, case, right? Yeah. A group that's not necessarily close to
Okay, so let's go ahead and thank Spencer again.